This is our first MCQ practice. It's the first 28 questions with no calculator, and this material was provided by Bryan Passwater. So we're going to get started here. I'd like you to do the same with me as you're following along. This is describing the function. So if a function is decreasing, that means from left to right it's going down. The first thing I'm going to do is I'm going to look at that. So this is not going down from left to right. I cancel it out. This is not going down from left to right. I cancel it out. So going down and going down. So I have two options right now. I have a 50% chance of getting this right. Now here's the key. Rate of change. When rate of change is increasing, we say it's concave up. When rate of change is decreasing, we say it's concave down. So I'm looking for concave up or that smiley face. I can see that in option C. All right, we're looking at average rate of change. And so we have a couple different ways that we can write this. And as we get into upper level math, sometimes we write it just a little bit differently. But you remember learning about y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's basically what I'm going to do. So interval notation, we may also see this as 1, 2, 6. Remember that this would not be considered an ordered pair. It represents the endpoints here of this interval. So what I'm going to do is I'm going to come up above and I'm literally going to circle 1 and negative 3, that's my first ordered pair, and 6 and 5, that's my second ordered pair. I'm thinking of this as x1, y1, x sub 2, y sub 2. And this is just too simple of a problem. It's very procedural. I want to make sure you don't get it wrong, and so I would definitely suggest you put your parentheses in here, and I'm going to drop this in. So we have y sub 2 is 5, negative 3 is going to be the y sub 1, and then we have 6 for x sub 2, and 1. And so we don't want to make a mistake here. We know two negatives make a positive. I have 8 over 5, and we can see the correct answer is D. All right, so we're going to touch now on, we're going to use end behavior, and I can see that we're looking at exponential functions. So let's just talk about this really quickly. Please write this down for me. When we have a function like f of x, we have this a value and we have this b value. This a value is our initial rate. This is the initial amount or initial rate, and then this b value is going to, it's initial amount, and the b value is the rate. So let's take a look at what this looks like. If I have a b value, that is greater than 1, it's looking like this. B value is greater than 1, it's looking like this. Now that's also true when my a value is positive. So I'm going to write a is positive and b is greater than 1. So from left to right, it's increasing. I can also see the rate of change is increasing because it's concave up. Thumbs up, thumbs down, if that makes sense. Okay, let's talk about this again. Now, what could happen here? If I have still a b value that's greater than 1, so b is still greater than 1, but the a value is negative, I really think you should be writing this down, then it reflects across the x-axis and looks like this. Reflects across the x-axis and looks like this. So how would we describe what I just did in blue? Would we say that function is increasing or decreasing? Would the light blue be increasing or decreasing? It's decreasing because from left to right it's going down. Would we say the rate of change is increasing or decreasing? So in my mind, I'm like, okay, is it concave up or concave down? Concave down, so the rate of change is decreasing. Okay, all right, so I'm going to get back to this. I just want to do a quick review then. Now, what else could this look like? So our other option would be like this. Here would be our other option. Here I have an a value that's positive, but my b value is greater than 0 and less than 1. So it's like 1/4, 1/2, those kind of things. And you can guess by now what happens when we have an a value that's negative, but we still have that b value that's less than 1 or greater than 0. It's going to reflect across the x-axis, and it looks like this. Okay, and you're thinking like, Ms. Bradley, why did you do all of that? I wanted to review that with you before I jump into this problem and tell you this is how I would do it. So I wanted to review this with you because I saw the number of hands that went up that got this problem wrong. Here's what I'm doing right now. I'm using this notation of end behavior to sketch a graph. So forget about these for a second. I'm making myself just a very simple graph. I can see if I have an exponential function, so it's going to mimic one of these 4 graphs. This says as I go to the far left-hand side, my function is headed up. As I go to the far left, without bound, my function is headed up. So I'm going up on the left. This says as I go to the far right without bound, I'm getting closer and closer to a value of 0. Okay, so it's looking like this. So now I have to know, okay, I can see what's happening. Well, if it's looking like this, and it's above the x-axis, I know my a value is positive. Ooh, a's not positive, a's not positive. Okay, positive, positive. But when it's coming down like this, that rate is between 0 and 1. So the value in between is less than 1 and greater than 0, making the correct answer C. Other way that I'm not going to take time to do that if you got into a situation, because how many of you by raise of hands that are present with me felt like you had enough time to do these questions? It's almost like either I knew the content or I didn't, right? So if you get to a problem like this and you have to come back to, you're like, I'm just not really sure, but I have 10 minutes left. What am I going to do? What I would do is I would make a chart. I'd make an XY chart. And I would start plugging in, like, I know it's not these two because of my graph, but which one is it, right? So you could plug in values. You could plug in like -1, 0, and 1 and start graphing it to see, does it match up with what you sketched? Okay, so you're going to go ahead, you're going to read number 4, and then we need to talk about when we take these exponential functions and we model them with word problems, we have things like this. So I'm just going to write this down right now. I have a, I have a rate, and then I have x over some number. So let me tell you what all this means. This a value, and I would write this down, unless you felt super confident with this, I'd write this down. That a value is what is your initial amount? What is your initial amount? This rate, you're always starting at 100%. And if you're gaining, you're going to add. Like if I said that you're going to gain 2%, then it would be like 100% plus 2%. Well, that's equal to 102%. And as a decimal, it'd be 1.02. If I said to you, I've not read this problem, but if I said to you, you're going to be decreasing by 5%, then you always start with 100%. I would subtract 5%, that'd be 95%. Written as a decimal would be 0.95. And we can see they're written as a decimal, correct? Okay, so that's just an idea. Now we're going to come over here. This is how often, I think that's very important you write this down. This is how often does this occur? And so now, this is where your test-taking skills are going to be to your advantage. Really take time to we are going to X out the ones that we know do not work. So I'm starting to read this here, and I see a decrease by 19%. So above this, please write 100% minus 19%. Okay, that gives me 81%, but as a decimal, that's 0.81. So right away, I cancel out A and B. I got a 50% chance of getting this right. It tells me that the value, initial value of the car is 30,000. Okay, I've got that down. Now, where they make the difference between option C and D is that how often does this occur? It decreases each year. It decreases each year, and years are going to be written as months. We know there's 12 months in each year. So how often does it occur? It decreases 19% per year. Again, it tells us to do it in terms of months. So on the bottom has to be a 12, and that's why the correct answer is D. Okay, so here we go. We got a domain. Now, I'm going to take that domain, and I want you to go above this and write this in interval notation just to recognize that depending on who the author is, I want you to know that in interval notation, we can also say it's -2 to 8. Those are endpoints. We're including that. That's not an ordered pair like a lot of students mistake it to be. Also, let's come over here and let's talk about this. Jump back to when you had Miss Castro. You were in freshman level algebra, and let's talk about what we know. This is talking about horizontal shifts. It's talking about what's happening horizontally. This is talking about we are dropping this whole thing down. So this is affecting our y values. We're dropping the whole graph down. Here we're going to stretch it, or it's going to rise at a faster rate. So this is talking again about stretching things. We're stretching things. It's rising faster over time, and we're dropping everything down. This is the horizontal shape. And what this says is, how is this going to affect the domain? When you think domain, do you think x's or y's? We think x's. So please go above this and write x's. We think x's. So I'm going to take, and I'm going to write this down. -2, and I'm going to leave some space here, and 8. And instead of putting an x here, I'm going to take this portion that's going to change the domain as we go from F to G and define G. And I'm going to put this in place. So we have 2x plus 4. And now I'm literally just going to do the algebra necessary to isolate the x. But some of you may be a little confused. Remember that when you are solving for a variable, we're going to do PEMDAS backwards. So in the middle here, is there any adding or subtracting outside the parentheses? There's not. Is there any multiplying or dividing outside the parentheses? There is. Opposite of multiplying is dividing. Every single one of these we're going to divide by 2. So we have negative 2 divided by 2 is negative 1. We didn't divide by negative, so I don't flip anything. And I have x plus 4, and over here we have 4. Okay, great. Then I'm going to subtract 4, subtract 4, subtract 4. I have negative 5, and x, and 0. And then there's another way, like I spoke about earlier, that we can write this. We can write this as the new defined domain for function g will run from negative 5 to 0. Here is a problem that I want you to practice. It is just like the one we went over. So I'm telling you that for f, we have a domain that runs from negative 3 to 6. Now, we're going to redefine what is the domain of g given this information. I'm going to press pause. I'd like you to do it, and then let's check our answers. This is a subtract one right here. Yeah. Yep. While others work on this in class, you may be thinking, like, how do I get this started? So the smaller number goes on the left, larger number goes on the right, x is in between. We know x has to be greater than and less than. Now that represents the domain for f. We're redefining what is the domain for g based on this information. This is going to be a stretch of 2 and reflected across the x-axis, but it doesn't affect the x's. This is going to be all points are shifted up vertically 4. It's not affecting the x's. This is what affects the x. So I'm going to replace this with 3, x minus 1. And now I'm dividing by 3. I have negative 1, x minus 1, and 2. I'm adding 1 to all sides. I have 0, x, and 3. And I would define the domain of g as such. Let me go over number 6, and then let us practice another example like it. So I ultimately want to find a way to simplify this. In fact, I want to find a way to evaluate the left, the right, and then add those values together. Notice that these log bases do not have the same base. So some of you may have thought, oh, aren't I supposed to like take this and compress it right now because it's an expanded form? No, can't do it when the log bases are different. What does this even mean? Well, let me just jump over here. If I said this to you, this would be in logarithmic form. We can rewrite this in exponential form. The base remains the same. So I have a base of 5. It goes across. It takes the value on the opposite side of the equal sign, makes it the exponent, and it comes back for the answer. So 5 squared is 25. We all agree with that. Okay, how is that going to relate to this? So let's look at this first part. If I take this and rewrite this, I'm going to say log base 8 log base 2 of 8 equals, I don't know what that number is, so let me write it in exponential form. 2 raised to the I don't know equals 8. So 2 raised to what value equals 8? You do not have a calculator, so they're going to have you doing mental math. 2 times 2 is 4. 4 times 2 is 8. This equates to 3, so I'm going to put a 3 above it. Okay, next up, I'm going to do the exact same thing here. I have log base 9 of 1/3. Equals, I don't know. I got to evaluate this portion of the expression. So 9 raised to what number equals 1/3? And that was a little bit trickier. So let me help you with that. I'm just thinking in my mind, how do I turn a 9 into a 3 using exponents? Well, I know that the square root of 9 is 3. And I know another way to rewrite the square root of 9 in exponential form is to write it as 1/2. Because remember, there's that little 2 that hangs out. So this is the same as 1/2. So knowing that, let's do that real quick. If I make this a 1/2, the problem is 3 is not on top, 3 is on the bottom. So I need to send it to the bottom. That means this value up here should be a negative 1/2. 9 to the negative 1/2 means, well, the square root of 9 is 3, but it needs to be put in a different level, not on top, but on the bottom. This portion right here is a negative 1/2. And now I'm just going to take 3 plus a negative 1/2. Let's find a good common denominator. And however you want to do this is really up to you. So we could go like this. We could go, okay, 3 times 2 is 6. 1 times negative 1 is negative 1. And divided by 2, we have 5 divided by 2. And our correct answer is C. I would like you to try another problem like this. So here is your problem. Please write this down. I have log base 2 of 1 over 16 plus log base 3 of 27. I'm going to press pause, begin. Okay, we're going to do one at a time. Ready? So I'm going to write this off to the side. If you're confused, you should do the same. Equals a question mark, and we're going to evaluate this part. And this equals a question mark. So I'm now going to write it in exponential form. So the base remains on the bottom. Whatever is on the opposite side of the equal sign becomes the exponent. I'll do the same thing here. 3 raised to the question mark equals 27. So I need to figure out, forget about the 16 being on the bottom. Forget about the 16 being on the bottom. I just need to figure out 2 times itself, how many times equals 16? So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So I like the answer of 4 here. But 4 by itself won't work because 2 to the 4th is 16. But where does the 16 need to be? On the bottom. So what do I need to do to the 4? It needs to be a negative 4. This is equivalent to negative 4. Over here, 3 times itself, how many times? I saw students as I walked around put a 9 here. Remember, this is 3 times itself. So 3 times 3 is 9, times 3 again is 27. So I'm going to take negative 4 plus positive 3 to end up with a negative 1. All right, let's look here. It looks like this is going to be a pattern problem. So we're looking at, let's see here. The graph we see up above is f, and then down below is going to be the inverse. So here's what I need you to know about inverse functions. Please write this down. If you happen to get 7 wrong or you had to guess, please write this down. When you look at an inverse of a function, the x and y values will flip. So the x and y values will flip. If this is f of x, then the inverse will have y of x. They're reflecting across the line y equals x is what's happening. So what I did is I look up here and I just literally choose 1 point. I'm going to see if 1 point can do it. This is the ordered pair 0, negative 1. So if this is on the graph of f, then I know the graph of the inverse must contain negative 1, 0. Let's find it. Does this have negative 1, 0? It could be the answer. Does this have negative 1, 0? Nope. This has to have negative 1, 0. Sorry, let me go up. It does not have negative 1, 0. Nope. Does this have negative 1, 0? Nope. We only have 1. Correct answer is A. All right, so we're looking at composite functions here, and we're literally just following this pattern. I'm going to write this out. Ultimately, I want to know what does h of 4 equal. That's what I want to know. But notice that there's no h up here. So in order to figure out function h, I have to know about this composite function. So I need to know what f of g of 4. So they're already telling me that my x value is going to be 4. So I'm going to evaluate this, and whatever I get for a final output goes right here because I can see the 2 are equal. So how do you evaluate a composite function? You always start on the inside and work back outward. So let's first find this. I need to know what is g of 4. What is the outcome? So what do? I find when x is 4, okay, got it, and I find g, and I literally keep going until I find, okay, the outcome is negative 1. This equals negative 1. Then I apply that to f. So what I do the exact same thing. Okay, I find negative 1 for my x, and I find f, and outcome is 2. That means this equals 2. Correct answer is C. That are watching this video, we're practicing another one just like this using the table up above. And so h is going to be defined by the function. So h of x is equal to this following composite function. And I want to know what is the value of h of 0. So those that are in class right now, you have 15 seconds. Go ahead, please. Hands raised when you have an answer. Okay, you ready? I do not want you looking up here. I'm going to explain for people that have to rewatch the video. I want you turning right now to people in your groups. You're going to turn right here. You can include Ethan as well. Turn to your groups. You have 20 seconds to make sure everybody understands this while I explain. Go ahead, please. Okay, so I'm going to replace this with 0. And then I start on the inside. So what does this mean? This means the x is 0. So I find 0, and I find function g, and I go, okay, the output is 4. Okay, the output is 4. Now I always work outside, and now I'm going to do the exact same thing. So now I'm going to find 4 for the x's, and I want to find function f, and the outcome is 3. So h of 0 equals 3. How many were able to get the following? H of 0 equals 3. Hands up high. I want you to right now go to next number 9, and I want you to write this down. We're talking about asymptotes, specifically horizontal asymptotes. So please write this down. We have 3 different categories. We have top heavy, we have bottom heavy, and we have equal. When we have a top-heavy function, so when the degree on top is larger than the degree on the bottom, that's what we have up here. Does everybody see how, excuse me, does everybody see how the degree is 3 on top and the degree on the bottom is 2? You're going to hear people say top-heavy degree. When the degree on top is heavier than the degree on the bottom, it's greater. There is no horizontal asymptote. We have a slant asymptote. But if they don't ask me to find that equation, we're not going to do that polynomial long division. Now, what happens when it's bottom heavy? And you're like thinking, like, what is she talking about? I'm just going to give you a quick example. If I had something like this, r of x equals, I'm making this up, 5x plus 6x minus 1 over 2x to the third minus 3x plus 2, or something like that, right? The degree on top is 2, the degree on the bottom is 3, so we're bottom heavy. The degree on the bottom is greater. We will always have a horizontal asymptote with the equation, the horizontal will always be y equals 0 every single time. Now, what do we do when they're equal? You're going to divide the leading coefficients. So again, I like examples. R of x equals 8x squared plus 6x minus 1 over, let's go, 4x squared minus 5x plus 2. Okay, I got a degree on top of 2. I got a degree on the bottom of 2. The degrees are exactly the same. So to find out the horizontal asymptote would be the equation y equals, well, 8 divided by 4 is 2. So let's come up to this equation. A rational function claims what about r? Okay, and I look down below and I can see they're all talking about horizontal asymptotes. So I'm going to analyze. It is top heavy. There should be no horizontal asymptote. So let's look. It has a horizontal asymptote? No. It has a horizontal asymptote? No. It does not have a horizontal asymptote. Why? Because the degree is greater on top in the numerator than it is in the denominator. All right, number 10. Number 10 is one of those questions you're like, what am I supposed to do here? And so look here. We are going to look over here at the sum and difference identities from our unit 3, our trig unit, and we're going to apply which one. So when I look here, I have the cosine, and I'm adding 2 things. So I come over here, cosine, I'm adding. I'm going to write this down. So it's cosine, and then it's sine, and they're subtracted in between. Let's write it down. So I'm going to write down, we have cosine, and I'm just going to put a right now. So cosine A, cosine B, subtract sine A and sine B. Now, A is going to be this very first thing for me. So A for me is going to be this, and B for me is going to be pi over 3. And I'm just going to drop this in now. So we have cosine, I'm not going to write cosine A, I'm going to do the symbol, and then we're going to multiply that by the cosine of B. Well, B is pi over 3 minus, now we have sine of the symbol times the sine of pi over 3. Okay, now pi over 3. Pi over 3 is in that first quadrant. It's a 60-degree angle. Some of you may think of it as 2 pi over 6. It reduces to 1 pi over 3. And this has the coordinates of 1/2 and square root of 3 over 2. So I get to evaluate this portion and go, okay, well, I know the cosine of this angle, the cosine is the first number, is 1/2. So it should be like 1/2 times the cosine of this angle. Let's check here. That doesn't have it. Ooh, that has it. That has it. I got a 50% chance of getting this right. Understanding what you can cancel out is just as important. Okay, let's do the next part. There should be a subtraction. Does everybody see that? There should be a subtraction. This does not have subtraction. I don't even have to do any more. But let's just say on a test they happen to have a few more options that were pretty close. You come up here and you'd say, okay, the sine of pi over 3, well, the sine of pi over 3 is square root of 3 over 2. And you can see this is how you're able to achieve the correct answer. So when I look at number 11, this is what I'm going to do. I'm a visual learner. That's how I learn. And so I'm going to come over here and I'm just going to draw a graph that kind of represents what I'm told. I'm told that P is positive. So do me a favor right here and just write above the x-axis. So the values are above the x-axis. That's what P means, positive. It also says it's increasing. That means from left to right, it's rising. It doesn't say anything about the rate of change. It just says it's increasing. So bless you. So I'm just going to randomly do that. So here we go. I'm going to go 2 over, and I'm just going to choose, like, here's my point, and there's 3, 3, and there's 4, 4, and here's 5, 5, and here's 6, 6, here's 7, 7. So there we go. I believe that my picture represents where P is positive and it's increasing. Done. Now it says to me, if this is an odd function, so here's where you're going to have to memorize this. So please write this down on this problem. And then we're going to talk about what does that even mean. And I'm going to personally draw a picture to represent this, or at least try to do that, and then I'm going to answer the question accordingly. Okay, so you ready? So I'm going to make my little table of values here, and I'm just going to start with 2 because this interval went from 2 all the way up. So let's go with 2 here. So I have x and I have y. Okay, so if I plug in 2, and this has to be true, if I plug in 2, what is the outcome of my 2? 2 has an outcome of what, guys? You got to pay attention here. So in this graph, if I go over 2, the outcome is how high is it? It's your y value. So what is my outcome? It's 2. Do you guys agree with that? It's 2. So my outcome is 2. This is what I had. 3 goes with 3. 4 goes with 4. 5 goes with 5. 6 goes with 6. 7 goes with 7. Now, if this is going to be the case, I need to take and I need to put a negative in front of the outcome. So now, watch this really quickly. So when I plug in a 2 here and I go, okay, what is f of 2? Well, the outcome of f of 2 is 2. So I'm going to put a 2 right here. But then there has to be a negative sign that drops down. And then I'm going to write a 2 here because I'm testing 2, and then I have to drop down that negative sign. So what does this mean? This means that if I go to an input value of -2, I'm going to get an output value of -2. If I go to an input value of -2, the output value is -2. Okay, I'm going to do 3 next. Okay, so I'm going to start with 3. I already know 3 goes with 3, so I'm going to do this. So I have f of 3. Well, what is f of 3? F of 3 produces an output value of 3. What's over here, guys? It is 3. So I know this part produces 3. So I have 3 here, but then I have to drop that negative sign. And she's like, where is the negative sign? Right there, there's a negative. I have to drop that negative sign down, and then I rewrite it as f of 3, but remember that negative sign. So what does this mean? This means go to an x value or input value of -3, and we get an output value of -3 as well. And you guys can understand we'd have -4, -5. So this is what I have. Now I need to evaluate this. So this is below the x-axis, so it's negative. I cross out the last 2. I can see that from left to right, it's increasing. There's only one option of increasing. And we also can see, by the way, it does go from negative x values of -7 all the way up to an ending interval of -2. Let's look at number 12. Okay, first thing I'm going to do, I'm going to expand this. So I'm not going to FOIL, but I'm going to write this out. So I have x minus 3 one time. I have x plus 2 twice, quantity squared, x plus 5, x minus 4. Please do the same in your paper if you have not done so. I have x plus 2, x plus 5, x minus 4, quantity squared. I'm going to write it down twice. Please do the same. Okay, now I'm going to see if I have a factor or a quantity on the bottom that's exactly the same as a quantity on the top. This could represent potential holes in graphs. So this is where I'm starting. Is there any groups of x plus 2 on top? There is. And I'm going to come off to the side. This could be a hole. I'm going to set it equal to 0. It could be. We'll figure out later on. Is there an x plus 5? There is. So x plus 5 could represent a hole. Is there an x minus 4? There is, and it's only a 1 for 1. So if you cancel a 1 on the bottom, you can only cancel 1 on top. So x minus 4 equals 0 could be another whole. So now let me write down what we have remaining. We have x minus 3, x plus 2 over x minus 4. That's what I have after I've done this simplified that a lot of you guys think about as canceling out. So here's how this works. You're going to identify the potential holes, and then we come back to the graph. We know we're in trouble. We know this function is undefined, and we have broken a math rule if the denominator ever equals 0. So some of you can just do this in your head. Others will do the math. But I am in trouble if x ever equals 4. This is a vertical asymptote. This trumps everything. So I figure out what are the potential holes, and then I come back off to the side, and before I declare the holes, I have to decide, is there a vertical asymptote? There is. How many vertical asymptotes are there? 1. Let's do this. 1 vertical asymptote. Oop, cancel. Oop, cancel. Oop, cancel. Oh, by the way, I don't even have to do any more work. Does everybody see that? And you're like, but why is there not 3 holes, Miss Bradley? If you solve this, you'd have x equals negative 2, x equals negative 5, and x equals positive 4. There can't be a hole where there's a vertical asymptote. This trumps it. This takes precedence. So that's why if we actually had to name them, we'd say, hey, there's a hole at x equals negative 2, there's a hole at x equals negative 5, but we have a vertical asymptote at 4. So if you did not know that, you're going to put that down. That a vertical asymptote will always trump a hole in a graph. 13 and 14, we can get through really quickly. We're looking down below, and all I want to know is what is the amplitude. So as a quick reminder, amplitude is we're going to take the maximum value, which happens to be 4, the minimum value, which happens to be negative 2, and I want to know what is the distance in between, and then I just divide it by 2. It's not asking me for the midline. So I'm going to say, what is this distance? Well, 4 minus a negative 2 would be 6. So this is a distance of 6. You cut 6 in half, and you end up with 3. So 3, I can go 3 up or 3 down. If they ask me for the midline, and it would be y equals 1. They're not asking. They're just saying, what is? Amplitude is the distance up or the distance down, always a positive value that represents from that midline to the highest or lowest. Correct answer is B. Thumbs up, thumbs down to your understanding. Okay. Here we go. Let's go to this one. There's a great chance that you saw this problem and you're like, I have no idea because it wasn't part of our curriculum. So you're going to take notes on this and we're going to go through this quickly. Are you ready? Okay. So when we talk about different models of equations are like linear. That's a straight line. You guys know linear, right? With your arms, what does quadratic look like? With your arms, go. Quadratic is like this, right? Quadratic? Yes, yes. When we think cubic, we think something like this. We have quartic that could look like this. So we have these different models. And when we're looking at real life data, and we have to be able to use the data to predict the future, they like it to be able to nicely match up with a model. Like, oh, this looks like it's going to be linear. Then we can create an equation that tells us what's going to happen in the future. Oh, this looks like it's going to model. So what they do is they use what's called this residual plot. And residual values is a way to measure how much our regression curve vertically misses a data point, or the actual measured data point subtracted from the predicted gives us the regression line. But here's the most important thing you're going to write down for me right now. Are you ready? Write this down. A good residual plot. In a good residual plot, the residuals have no clear pattern. Please write that down. If they give us a residual plot, it's going to look like Miss Bradley just went and played darts, and I'm horrible at darts, by the way, okay? For some of you to know, I'm not good at throwing. I'm not good at accuracy. So if you see a residual plot and they say, is this a good one for a particular model? If you can see any type of a pattern, you know it is not. So like this, can you see any pattern here? Can you see any pattern? And we can't. So we know that's good. That's good residual. It's going to match up with a model. Let's come down here. Can everybody see how we have a pattern here? This is not. Can we see how we have a pattern here? This is not. So let's look over here. I just gave you some more. Here I can see a pattern. This is not. This is not going to be good. I can see a pattern, not good. I can see a pattern, not good. Does this have much pattern to it? Not really. So this would be a good residual. Let's come back over here. So we want to know, they already tell us that we want to look at the residual model and see, is it good for a linear function? Okay? So our linear regression function. And so, by the way, do you guys see a pattern? Yes. Can you see a basic pattern here? This means it's not good. It is not good. So let's find out which one says it is not good. The linear model is not appropriate, so we can cancel this out, and we can cancel this out. And why is it not? Because there is a clear pattern that tells us it's not good. Because there is a clear pattern. Whenever we see a clear pattern, we know it does not fit a particular model. That's why. All right, let's look at 15. Let's get this done in 15 seconds or less. So I want to know, where do these two functions cross? Whatever they cross is going to have an x and y point on a graph. By setting them equal and solve, I can find the x. So 2 sine of x cosine of x is equal to negative sine of x. I'm going to move this to the opposite side by adding, excuse me, I have 2 sine of x cosine of x plus sine of x equals nothing. Now on this side, notice the left and the right both contain a sine, so let's factor out a sine. And I'd be left with 2 cosine x plus 1. Now I'm erasing. Let's make sure I did this right. Multiplies, that looks good. Multiplies, that looks good. What am I going to do next? I'm going to take each one of these quantities and I'm going to set it equal to 0 and solve. So sine of x equals 0 and 2 cosine of x plus 1 equals 0. What this means is when I go once around the unit circle all the way up to, but not including 2 pi, where is the sine equal to 0? Sine is equal to 0 here at 0 and also over at pi, where we have the ordered pairs of 1, 0 and of negative 1, 0. So I want to look up above and find 0 and pi. Let's find that. This does not have 0 and pi. This does not have 0 and pi. Okay, I have a 50% chance of getting it right. Like, you don't understand how much you are going to increase your chance of passing this test by eliminating the wrong answers. Okay, let's do the next one. Now I'm going to go really quick here. I'm going to subtract 1 to the opposite side and then divide by 2. So I get the cosine of negative 1/2. Now, let's see what we can do here. I want you to think smart. Where are cosine values negative in which 2 quadrants? Answer for me. Which 2 quadrants? 2 and 3. So I'm going to come over here and I want to know, is this in quadrant 2? Yes or no? Boop. Is this in quadrant 2 and 3? I don't have to do any more math. Done. Let's look right now at number 16. I went ahead and I graphed those ordered pairs, and then I'm going to connect them, and I can already see that we have a concavity of concave down, so the rate of change is decreasing. So I come over here, concave down, I have a 50% chance of getting this right. Now I have to really pay attention to what it's saying after this. So it's saying the rate of change, so here we go. Is the rate of change decreasing? Is that what makes the concavity go down? Or is the rate of change negative? And the rate of change is what? What do we say when its concavity is down? We say it is decreasing. We say it's decreasing. That's why we're going to get an answer here of D. Those that just came in, do you want me to go over 16 in 20 seconds quick? No? Yes? Okay, I graphed the ordered pairs really quickly. I can already see this is concave down by graphing it. So I eliminated A and B. And then they're asking, why is it concave down? Now, I know it's concave down because the rate of change when concave down is, the rate of change is decreasing. Here, rate of change is decreasing. Okay, so I see a function that has a degree that's 4. When we have degree 4, we have an even function. Please write down even function. So even function means the end behavior on both sides is either both going up or both going down. So hands are up. If you think of this, your hands are going up, or both going down. But because it's negative, it means it's down on the left and it's also down on the right. So something's happening here, and it's looking probably something like this. Okay, it's looking probably something like this. Now I got to go up here and see what we're looking at. So there should be no global minimum because these arrows mean that it goes down continuously. So as it moves to the left without bound, it's decreasing. As it moves to the right without bound, it's decreasing. So here we go. The function has a global minimum. Nope. The function has a global maximum, but it does not have a minimum. That looks like it could be. It has both a minimum and max. Nope, can't have a minimum. It has neither a minimum or a maximum. Wrong. So if you're like, what would it look like if it didn't have a minimum or a maximum? It would look like an odd degree function like this. So here's where you don't have a global maximum or a minimum, because as you move to the right without bound, it's going up, and as you move to the left without bound, it's going down. There'd not be one and one single point that stands out as the highest or lowest. That leaves us with option B. So I'm able to get this question myself by graphing this to best understand this. Let's look at number 18. So I'm coming in here right now, and I'm just going to do a rough graph of this. So what does this mean? Like, I personally like to write this as positive 52 and back. So that means we're shifting everything up 52. So I'm just going to do a rough graph. So here's what I have. I shift everything up 52. This is going to be like my new x-axis. This tells me that I have a normal cosine function. By the way, remember, cosine functions look like this, right? You guys know that? Cosine functions looks like this. But, when the value up front is negative, instead of starting up at the top of the hill, where does it start? So it starts like this and goes like that, right? So I'm going to make that right now. So it's looking like something like, oh, and by the way, I have to go 27 above and 27 below. Okay, so can you do me a favor? I need to know help me out here. What is 52 plus 27? Because that's how high up it goes. It goes up to 79. So it goes up as far as 79. And then what is 52 minus 27? Oh, I'm having to do some elementary math here that I'm not good at. It goes down as 25. So I know this is not drawn to scale, but it's looking like this. It starts like this, and that is going to be one cycle. Does everybody see that? One cycle. Now, we need to know, what is the length? Well, in a normal cosine parent function, y equals the cosine of x, you're going to take 2 pi, and you're going to divide it by the value that's directly in front of the x. In this case, on this parent function, it would be a 1. You divide by 1, and you go, okay, one cycle of this function would be a distance horizontally of 2 pi. But here, we're going to take, and I'm going to do the math over here, I'm going to take 2 pi, and I'm going to divide it by whatever stuck in front of the x, or in this case, it's the variable t. So I'm going to divide by pi over 15. Now remember, when you divide, division turns into multiplying, and I flip the second, and so this is what I have. I have 30 pi over 1 pi. Well, 30 pi over 1 pi reduces just to simply 30. That means this length of one cycle is a length of 30. Now let's go back to what this is even talking about. This says, for which of the following is the maximum number of customers inside the restaurant? So if this represents the number of customers in the restaurant, I could see that right here, right at 15, and this talks about t is in time. So at 15 minutes, they hit a maximum number of customers. Does everybody see that? Are you guys listening over there? Or are you just talking? Okay. What is the maximum number of customers? So we're going to take this 52, and then we need to add to that. It should go all the way up to 79. And by the way, that happens 15 minutes in. Okay, so here's your reminder you're writing down. If number 19 tricks you, this is what you're writing down. You're writing down that complex roots always come in pairs. Complex roots always come in pairs. So you're like, Miss Bradley, what does this mean? So if this is one complex root, please write this down. Here's the other one. They always have to come in pairs. They look exactly the same, but one's positive, one's negative. What this says, and by the way, complex roots, we can't see it as actually x-intercepts. They're hidden. They're imaginary. If this is one complex root, then here's another one. So I already have 1, 2, 3, 4. I have 4 complex roots. Now I'm going to come back over here. And do you remember how, as a quick reminder, I'm going to make just 3 graphs here. Do you remember how I told you how when it's degree 1, how it just cuts straight through? If it bounces off, we say it's degree 2. Do you guys remember that? And then if it makes this like little snake through, we say it's degree 3, correct? So what is this? What would we say this is? Degree 1. Okay, so I'm just going to write degree 1. And what would this be? Degree 2. So I got to count. There's 1. Okay, there's 2 more. So I'm up to 5, 6, 7, 8, 9. What did I count wrong? 1, 2, 3, 4, 5, 6, 7. I totally counted wrong. We are getting down there. Number 20. So here's what we're going to do. We can see that one cycle, underline this, is 11. So every 11 we see the exact same thing happening. So here's how I did it, but I'm guessing there's many ways. There's probably algebraic ways that are even prettier, but this is why I did it. Every 11 we're going to start again. So 11, there's the first. Now I add 11, we're at 22. I add 11, we're at 33. I add 11, we're at 44. But I'm like, whoa, I don't need to go that far. I need to backtrack too. Does everybody see that? I need to backtrack too. So I know that this will have the same output, the same output, and the same output. So if I have to backtrack too, then backtracking to 42 is the same as backtracking to 9. So I find 9, what's output? The output is 2, correct answer is B. I'm a visual learner, you know this by now. And so it gives us an end behavior, and then we want to look up top and we go, okay, what should the degree be and what should be the leading coefficient be? So make yourself a little XY chart here if you guessed on this or you weren't confident. And now we're going to apply, what does this mean? So this is one way to write end behavior. This says as we move to the left without bound. That means we're going to the far left. We continue to go to the left. Our function is headed up. So go like something like this. Now, as I go to the far right without bound, our function is headed down. So I know right off the bat, because I have memorized the patterns of polynomial functions, this means when they're going in different directions, it means the degree has to be odd. The degree is my n, so n must be odd. That's odd, that's not odd, that's odd, that's not odd. I have a 50% chance of getting this right. When we are up on the left and down on the right, it also means the leading coefficient must be negative. There's only one option, option A. Okay, let's look right now at number 22. I'm just going to do a rough graph of this, and then I'm going to look over here. I bet you many of you didn't even have to do that, but that's just how my mind works when I'm doing this. So I know really quickly, I know that normally we'd be like this. When I have that b value, that's between 0 and 1, the rate, it's going to be an exponential function that's looking like this. It's a decay function, but because I have that -3, instead of starting above the x-axis, it's going to be right down here. It's reflected across the x-axis. So here's the general shape I have. Now, if you didn't know how to do that, you would take your xy and you literally start plugging in points and plugging them into the graph and then graphing it so you can see what does this look like if you had not memorized that. Now, let's look here. We're looking at this graph down here. I can see that this is concave down. So I'm crossing out A and I'm crossing out C. And from left to right is going up. It's increasing. Correct answer for number 22 should be B. That's how I achieved the correct answer, but as I've said to those in front of you, there's got to be a better way. In fact, probably doing a number line and testing things would be better, but just go with this, okay? Go with this for me right now. So I'm going to write the top one in here. So on top I have, let's see, I have f, so I have x cubed minus 3x squared minus 10x. On the bottom I have x squared minus 6x plus 5. I can see this is top-heavy degree. That means we have no horizontal asymptote. We are going to have a slant asymptote. Also, I want to factor this. I can take out an x. If you haven't done this, please do the following. We have x squared minus 3x minus 10 over x squared minus 6x plus 5. This goes back to what your Algebra 1-2 teacher taught you. And this factors into x minus 5 and x plus 2, along with x minus 5 and x plus 1. Okay. Good to go. Now, as a review of what we did about 10 problems ago, we're always going to first see, can I simplify things? That's determining, is there a hole? Ooh, I think there's a potential hole where x equals 5. I'm not declaring that yet. And then I come over here and I'm like, okay, look, we can never have x equal -1, because if that happens, we're in trouble. We have an undefined function where x equals -1. There's going to be a vertical asymptote. So I'm going to come over here. And I'm going to go and draw this little graph, and I'm going to go to where x equals -1. Because these are not the same, this also tells me right here that I'm going to have a hole at 5. So 1, 2, 3, 4, 5. There's going to be a hole. And now you can determine what would be the y-coordinate. So somewhere along here, there's going to be a hole in the graph. And you can determine the y-coordinate by coming back up to this graph, x times x plus 2 over x plus 1. So it's the simplified one, and I can substitute in 5. So I have 5, well 5 plus 2 is 7, and 5 plus 1 is 6. So I have 35 over 6. Okay, remember I don't have a calculator. I got to do some math here. 5 can go in 7 times. If you see me do something wrong, just let me know. Okay, so like 7.2. So I know up here at 7.2 is going to be a hole. That's what I know so far. Now my whole goal is, where is the function greater than 0? So if there's a hole here, do you guys understand how the graph is going to look something like this? There's going to be something, right, that connects to the left and right of that hole. And does everybody see how that's above? Does everybody see that? So look at my options right now. Do you see how it says, hey, we go up to 5? Does everybody see this? We go up to 5. And then we got to skip over it because there's a hole. How many of them have that option? One has that option. Done. Only one of them has that option. Now, if that hole had been below the x-axis, I could not have. Now, I went as far even to figure out what is going to be the equation of the slant asymptote, and I graphed it, and I graphed points. Can everybody see this? and I graphed points, and so I ensured, but when I went back and I was like, hey, test taking tip, there's only one option that looks like this. I don't have to do any more work. That right now, number 24, let's see here. We have a vertical asymptote at 1, we have a hole at -1. Okay, you ready? So I'm going to start here. I'm just going to go from left to right, and I'm going to simplify right now. Let's start here. So watch, I can simplify this. What does this mean? That means x plus 1 represents a potential hole. It doesn't mean it's going to be a hole, because remember, your vertical asymptote trumps if there's a hole, if they happen to be in the same spot. So -1, x equals -1. I believe this has potential for a hole. Potential. And so once I simplify, I'm still left with x minus 1 as a factor on the bottom. So I set it equal to 0. And then on the bottom, I can see that we have a vertical asymptote at 1. These are different numbers. If they don't conflict, they're not the same number, then they both are true. We have a vertical asymptote at 1. We have a hole at -1. Is that what it says? We got lucky. It's the very first one. Okay, you are trained for this. You know this. So I'm going to write this out. If you are not comfortable, I'm taking that quantity and writing it twice. Watch. 1, 2, 3, 4. I have 4, so I know it's going to be x to the 4th. What does that tell me? It's even degree. It's either both going up or both going down, but they're not going in different directions. For that reason, I get to cross out A. So they're either both going up or both going down. Now, how do I know they're going down? Because the leading coefficient is negative. Both going down. It could be B. It's not D because they're going up. So I have a 50% chance of getting this right. Now I go back to what I know. I know 0 should be, okay, I've got a 0, I've got a 0, okay? I know that x equals -3 should be, okay, that's good. This is not good. Correct answer is C. Relate this to quadratics and square roots, and I was going to have you see the difference in them. When you look at this function, we normally see the x values or the input values, and they normally are going up in even intervals. So normally it's like 1, 2, 3, 4, or 2, 4, 6, 8, right? Does everybody see that? Yes? When that has been flipped, and when we see, in fact, the output values going up evenly, then we're going to look at the input values and we're like, well, what are they going up by? Oh, that's times 2. Okay, that's times 2. That's times 2. So instead of this being exponential, do you guys remember what is the inverse of exponential? Logarithmic. Did everybody hear that? So if I gave this to you like this, switch this around and actually just write this down so you can see. This is absolutely, I'm going to give you some other numbers. We're going to try 3, 9, 27, and 81. This is an example of exponential. How do I know it's exponential? Because I can see the input values are consecutive, and the output values, in fact, are going to be modeled by a ratio of 2. That's an example of exponential. When that order is flipped, and you're like, oh, this doesn't look normal, my outputs are consecutive, and they may go up by 2s or 3s, but it has to be consecutive, right, in order. Then you look at the input values, and you're like, well, what's happening? Here I'm multiplying by 2, so instead of being exponential, it's logarithmic. So let's see what we can do. We can cancel out A, and we can cancel out B. Now let's look at the wording. The wording for number 26 is the part that matters that we need to slow down on. The input values over the equal length output, that's true, equal length output values are proportional. That means proportional means we're multiplying by the same amount or we're dividing by the same amount. So yes, the input values, while we work with output values that are in equal lengths, are proportional. So inputs are proportional. We're being multiplied by the same value for the inputs, and our output values, again, are going up in equal intervals. We have a correct answer of D. If you happen to be gone yesterday or you didn't watch the video, then I'm going to guess 27 and 28 were tough for you. I'm just curious. Let me press pause. 27 and 28. So I want to know which of the following represents this point P. Okay, so here's what I'm doing. I'm going here, and I'm like, where's 5 pi over 6? 5 pi over 6 is right here. And then I'm making this little line here. And why I'm doing that is if the R value, remember this is R theta here for polars, if the R is positive, I go towards that point. If it's negative, I go away a distance of 3. So distance of 3, 1, 2, and 3. Here is my point P. And I just need to go one by one until I find out which one works. So let's try here. So where's 7 pi over 6? 7 pi over 6 is right here. I can see it doesn't matter if I go front or back, I'm not going to land here. 7 pi over 6, again, whether I go front or back, I'm not landing there. Here's 11 pi over 6, which is right here. But to get to point P, I have to have it positive, which gives us option D. So the takeaway from yesterday is when I see something lined up with the x, we know right away x-axis, it's cosine. This does not line up with the x, so I'm going to go ahead and I'm going to cross out option C or D. It's not cosine related. It's sine related, but if it's going to be that positive value directly in front, that R value, it's going to go towards the top. If it goes down, it's going to have a negative value directly in front, and that's why we choose option A.